Hi, my name is Liam O'Brien from Turning Point School. For my project, I designed a foolproof timer switch for greywater systems. California's water use is causing environmental disasters like these. We must cut back on water use. Greywater is shower or laundry water recycled for irrigation. It is a powerful way to conserve water and deal with the drought. By capturing and measuring water from my shower and laundry, I estimate that families could save 12%, which is similar to the 15% Governor Newsom has asked us to cut back by. Greywater systems have an electrically controlled valve under the house to choose if water goes to the garden or sewer. But you need to be careful not to send bleach or cleaning chemicals to the garden. Otherwise, you might poison your garden. My circuit avoids these problems by automatically resetting the valve back to the sewer after each use. It is 3 stages that happen in sequence. Turn to the garden, wait, turn back to the sewer. I used 555 chips to time these steps because there's a lot of information on how to use them in books, websites, and YouTube. I even used one in my snap circuit kit once. The picture shows a single 555 timer with the schematic at left showing how it works as a single shot timer. The circuit has 3 555 timers, all powered by 9 volts DC. When I hit the button, the first timer activates a relay, which lets 24 volts AC turn the valve motor to the garden. The second timer just waits. It can be wired 8 minutes for showers or 45 minutes for the laundry. For demonstration purposes, I've set this one only to wait 10 seconds. The third timer uses a second relay to let AC turn the valve back to the sewer. Limit switches inside the actuator stop it in the correct position to line up the pipes. I can control the time each timer stays on for with this timing resistor and this timing capacitor. As you can see, this more or less works. I did many measurements testing parts of this circuit. The most interesting were of the time that each timer stays on. My hypothesis was that they should follow the equation T equals 1.1 times R times C, shown here as red lines, which is the time it takes to charge to move through the resistor from the source and to charge the capacitor up to 6 volts. The measurements were taken with a stopwatch, R in blue, repeated 10 times each so I could estimate the errors. In case I changed either the timing resistor in one plot or the timing capacitor in the other. These are the times relevant for turning the valve to the first and last stages. They agree with the line well enough that I accept the hypothesis, although it runs a little long. But for my 8-minute and 45-minute timers for the second stage, it took much longer than expected and was not repeatable between measurements. In this case, I video recorded the long timers to figure out how long they stayed on for, and repeated each measurement 50 times. These are histograms where the horizontal axis shows different measured times, and the vertical shows how many each time was observed. The red line are the hypotheses, which I reject in this case. I did other measurements on the effect of the in-between capacitors, whether the 555 output voltage was always larger than the voltage required to activate the relay, but they agreed with my hypothesis, so they were less interesting. I did some follow-up measurements to try and understand why timers always ran long. Most of my measurements didn't reveal anything, except these ones here. I speculated the capacitors might leak charge, which would force the timers to take longer to charge the capacitors up to 6 volts. To test this, I charged up a timing capacitor, removed the battery, and then video recorded a multimeter measuring the voltage for a couple of hours. The red line shows how the voltage would change with the time without a leak, but the data showed the voltage dropping off, indicating a serious leak. The triangle shows the time when half the charge was lost, and I repeated this 50 times and made a histogram of time to lose half the charge at right. This time changes a lot from one measurement to the next, and is probably responsible for my timing errors. The fact that the times vary from 46 to 54 minutes strongly hints that I responsible for the timers have non-repeatable times. I never would have seen this had I not repeated my measurements dozens of times. In the future, I may redesign this circuit to work around shorter timers to avoid capacitor leaks causing problems. I'm sure I'm currently playing with the Pulse 555 timer and the decade counter chip like this to make a more digital version of my middle stage timer. At 1 second per pulse, capacitor leakage should not be a problem. Please come by my display to discuss how I designed this circuit and my other measurements. Thanks, Liam out.